Okay, welcome. The floor is all yours.
Okay, well, thank you all for coming back for a third helping. I appreciate it. So my first lecture, I gave some structure, and I then described a completely combinatorial chain complex associated to a knot. And then I continued with that mostly during my second lecture, and then at the very end I started mumbling about holomorphic curves. So sort of historically, this holomorphic curve story came first, and the combinatorial reformulation that you all saw was a reformulation of this holomorphic story in a very specific example, which is for knots embedded in the three-sphere. It was a wonderful combinatorial formulation because you could understand all the components very concretely. Its problem is that the chain complex that I'm describing is gigantic. So that, for an n-crossing knot, you have like n plus 2 factorial generators. So we're going to take a homology of a chain complex, which is n plus 2 factorial dimensional. That's pretty daunting. So that's one of the sort of prices you pay for having such a simple differential. There is so Floer homology, not Floer homology, and Floer homology has various kind of elaborations where you allow certain kinds of holomorphic disks and disallow others. So for I guess the simplest example we saw even the first lecture was that you could set a u variable equal to 0, and then you got this not invariant, which I called HFK minus. So let me just step back. So Heegaard Floer homology is the homology of a chain complex over a polynomial algebra in a single variable u. So this is an invariant which one might call HF minus. You can set u equal to 0 and then get a simpler theory, which we call HF hat. And we saw already manifestations of this kind of simplification. When I talked about grid homology, that was also a modulo over a polynomial algebra, and you could set u equals 0 to get a finite dimensional creature. This specialization is good enough for many of the three-dimensional applications, but if you really want to understand four manifolds, then the minus theory is the one that you want to really understand. So what I'd like to try to describe now is, so we have a chain complex associated to a closed three-manifold. What I'd like to try to describe it are what are the sort of functorial properties of that invariant. So what happens if you decompose a three-manifold into two pieces? What kind of object do you associate to those pieces? And that story is called bordered Floer homology. And for HF hat, that was worked out mostly in around 2008 or so by Robert Lipshitz, Dylan Thurston, and me. But the story for HF minus is still under construction. So let me come back to that, and let me give you the outlines of what the story is. So the story we would like is, we want a way of constructing, so what happens if you decompose a three-manifold? So if you decompose a three-manifold, we've been talking about Heegaard diagrams, but you could think more generally. If I have a closed orientable surface that decomposes your three-manifold into two pieces, how would you be able to reconstruct the Heegaard Floer homology of that three-manifold in terms of invariance associated with the two pieces? Sort of like a Mayer-Vietoris sequence, if you like. So the the formal picture you would like is you'd like to associate to an oriented surface, maybe with some additional choices. But let's just say for an oriented surface for the moment, we would like to associate an algebra, which might be a differential graded algebra. And maybe I'm working over Z mod 2, so the gradings don't play as important a role. And then to a three-manifold with boundary, I'd like to associate a module over that algebra. Say a right module over that algebra. And to a three-manifold with boundary minus f, I'd like to associate, well, another kind of module, which is now a left module over that algebra. And I want to be able to reconstitute the Floer homology, but if I've got a closed three-manifold, that's a union of these two three-manifolds, then I would like to associate to that, I would like to say that I can compute the hat chain complex of this union of two three-manifolds glued along a surface. I would like to sort of an algebraic way of constructing that. I'd like to say that it's the tensor product of these two modules, some tensor product over A. This is the formal picture that we would like, and now let me just add a few moments of precision here, which is I don't just want a three-manifold with boundary, but I want with boundary homeomorphic to my surface, but I want an actual surface, and I would like a homeomorphism from my actual surface to the boundary of that three-manifold. So this is a bordered manifold. So you can't, I've got two three-manifolds with boundary that are homeomorphic. I can't glue them together to get a well-defined three-manifold. But if I have a three-manifold with boundary and I have a particular homeomorphism of my favorite surface to the boundary of this one and to the boundary of that one, then I can glue. That's the data I need to glue. So I was being a little sloppy. I want to actually choose a diffeomorphism between my given surface F and the boundary of Y1, and similarly for Y2. Except there I want the diffeomorphism orientation reversing. Now, what I want is, I want to now say that a small elaboration of this picture should then give a computational scheme for understanding three-manifold, for computing Heegaard Floer homology, because what happens if I were to try to change this parameterization? Okay, so why do I care about changing this parameterization? Because as we explained, every three-manifold has a Heegaard diagram, has a Heegaard decomposition, which is to say, there's a very simple standard three-manifold with boundary here, another one here, and I'm gluing them together along some interesting diffeomorphism. So I would like to figure out how the change of parameterization changes the bordered invariant. And that's answered by a kind of elaboration, a small elaboration of that picture, which is, suppose here's my three-manifold Y1 with boundary, and now I'm going to take surface times an interval. And I'm going to, but I'm going to parameterize it. Here's my phi, I'm going to use the same phi over here. And now I take surface times interval, I'm parameterize this by phi, and I'm parameterizing this by psi, some other diffeomorphism. Then associated to this creature, which is topologically very simple, if I forget about parameterization, but I shouldn't. And then I should get a bimodule here. So this is somehow like the bimodule of, this is like the bimodule of associated to this different diffeomorphism psi. And what we then want to say is that if I'm interested in the Floer homology of my three-manifold, after I change my parameterization by phi, well, that should just be So I should put phi into my data here. This is going to be C composed with phi. So that is to say, changing the parameterization just amounts to tensoring with this particular bimodule. And now, if you want to compute Heegaard Floer homology of anything, then what you do is you take your mapping class, which is specified by the Heegaard diagram, you decompose as a composition of very simple diffeomorphisms, maybe Dane twists or something like that. And then once you've decomposed it, then your three-manifold invariant can be computed by, you take the standard handle body with the very standard boundary parameterization, you blob onto that, you tensor it with a bunch of bimodules associated to Dane twists, and then you close it off with the three-manifold, and that should then describe for you the Heegaard Floer homology of your three-manifold. So this is, yes?
So could you describe what this bimodule is for?
No.
Okay, great.
It's a magic bimodule. You want there to be a bimodule that has this property.
I assume that this A or F.
What's that?
This algebra that is differential graded algebra that
Yes.
I suppose you're going to describe, that is acted on by the mapping class group of.
Yes, that's right. In the following sense, to every mapping class group element, you have a bimodule. That's the sense in which the mapping class group acts on that algebra. So that when you tensor two of those bimodules together, that's the bimodule associated to their composition. So it's a sort of categorical action of the mapping class group on that algebra. Any other questions? Okay, so this is the picture that we would like. For the hat theory, we actually worked this out. So for HF hat, this is an honest differential graded algebra. It's a little complicated to describe. It is associated to, I wanted to say that it's not associated to a diffeomorphism class of surfaces, but it's associated to an actual surface. And for us, an actual surface is specified by a handle decomposition. So we don't just associate to a surface, but rather to a handle decomposition of the surface. So I want to take the, we call them pointed matched circles, but what you do is you take the disk and you attach to it handles so that you end up with a circle, and then you close that up with another disk. So that's equivalent to saying that I have a handle decomposition of my surface with a single index 0 and a single index 2 critical point. And that's the data that I'm going to associate an algebra to.
So your handle decompositions have minimal numbers of handles.
That's right.
Could you associate an algebra to a handle decomposition with more handles?
Yes. Yes, you could do that. I guess we didn't do that for the hat theory at that time. I think now we probably could do that. So now, this is like a funny kind of invariant of surfaces, which is that if Z1 is a handle decomposition of a surface, and Z2 is a handle decomposition, another handle decomposition of the same surface, then their algebras are not quasi-isomorphic. Their homology groups might even be different. But there's an equivalence of categories. There's a bimodule that goes from here to there. And tensoring with that bimodule gives you an equivalence of categories. So this is a kind of funny way in which this is an invariant. Okay. And now I want to clear up a bunch of white lies. So the first white lie is that this is not a right A module in the traditional sense, but this is a right module in a sense which may well be traditional in the University of Chicago, which is that this is an A infinity module over this differential graded algebra. So I'll draw pictures of A infinity modules for the low dimensional topologists like me, but many of you probably have these sorts of things for breakfast. And this is another kind of algebraic object, which in some moral sense is a free module, but I'm going to make that precise for some sick reason. But that's a kind of module that will tensor product neatly. Yes.
Just wondering in general, you're saying that the category is the thing that's sort of canonical and not
Yes.
the algebra?
That's right.
Is it possible to sort of, for example, describe objects of the category or the natural sources of objects of the category?
The objects of the category are modules over that algebra. They're A-infinity modules over that algebra. Now,
I guess maybe geometric sources of objects.
so three manifolds are geometric sources of objects. They're not the only sources of objects, and I'm not an algebraist, so I can't surely there are some sort of theorems about what all modules look like, but I'm not one of those kinds of people. Okay. The other point is that I was saying that this story for the minus theory is under construction. What I'd really kind of ideally like to talk about is what we're working on right now. We were looking at a very special case where the surface in question is just the two torus. And so that's never going to compute arbitrary three manifolds, but it'll give some insights to what to do. So in the case where the story I want to tell, and I don't know how much of it I'll manage to tell, is also joint work with Robert and Thurston. The story I'm going to tell is not the only story for doing this. So there are other interesting approaches, one due to Ian Zemke, and another one due to Hanselman and his collaborators. I'm not competent to talk about those things, but I do encourage you to invite these people to give talks. They give beautiful talks about their approaches. But I'd like to at least to some extent describe what we associate to the. So I mean, I could tell the story of an arbitrary surface at the hat theory, which is a nice DG algebra, but instead I prefer to talk about this sort of case of the torus boundary, which is meant to work in general. Okay, so this, however, this is no longer a DGA. For the minus case, this is an A-infinity algebra, and in fact, it's more than an A-infinity algebra. It's an A-infinity algebra it's what we call a weighted A-infinity algebra. Okay. Any question? I'm going to define these algebraic objects shortly. Any questions before I start doing them? Okay, let's start with A-infinity algebras. Raise your hand if A-infinity algebras are common in your life. You could have raised your hand. Okay, all right.
I have just a question, hoping that the answer turns out to be simpler than what you're talking about, which is, so there's this sort of picture that some people are really into, where you look at these extended TQFTs, and the lower the dimension gets, the more complicated the algebraic structure. And I know that you want to, maybe you can already have a picture for four manifolds. What are the algebraic objects simple enough to understand?
Yeah, they're numbers.
All right. Beautiful.
So that's they're numbers. For three manifolds, they're vector spaces, maybe graded vector spaces. For two manifolds, they're algebras, and one can ask what's for circles, and there's a paper of Manolescu and Douglas and Lipshitz where they're sort of trying to work out, go down to circles, which I, again, they'll have to explain that.
So we want numbers we can get at some point.
We want numbers we can get. That's right. Ideally. Right. Okay. So all right. So let me start with A-infinity algebras. So A-infinity algebras. These are somehow very basic algebraic objects. So let me start by talking about differential graded algebras. Except since I'm working in Mod 2, some of the graded aspect is not so important. What's a differential graded algebra? it's a vector space A equipped with a differential, which I'm going to write as mu1, and a multiplication, which I'm going to write as mu2.
Well, why are you saying grading is inessential? The signs are gone, but the grading is still there.
Yeah, unfortunately, the grading is not by z. By z, by the integers. In our case, the grading is by a non-abelian group, and it's not the sort of thing that I would want to talk about in public. So there's you can forget about it at a z2 grading. So that's an object. The other thing about it is z2 graded. Okay, so there's a differential and there's a multiplication, and the differentials, and I'm going to draw these by drawing little trees. So the differential I'm going to represent by just drawing a vertex. I've got this graph with one incoming algebra element and an outgoing different algebra element, u1 of that. All right, it's a differential. It satisfies d squared equals 0. Which I'm just going to draw this way. Dot equals 0. It has a multiplication operation, which I'm going to represent by this kind of fork with its middle, like this pronged feature. And it satisfies a Leibniz rule, right? So A times B, so I get this multiplication, and it satisfies a Leibniz rule, which is like dA plus dA times B plus A times dB is equal to the differential of A times B. Right? And it's associative, which I can draw it as this. Well, these are the relations that a differential graded algebra satisfies. And the exercise one's supposed to play is, what happens if our algebra, rather than being associative, is only associative up to homotopy? So that is to say, I should have a homotopy operator. I'm going to write it as mu3 from A tensor A tensor A. And I'm going to draw it by this trident. And rather than having this being actually equal to 0, I want it to be null homotopic, which, a Leibniz differential. So that's going to be 4 terms. Differential of the first term, differential of the second, differential of the third, or differential of the output. And again, I apologize to the Lord of Science for having done this. But this is now this sort of more general, kind of generalized associativity property that you want. This gives you associativity up to homotopy. And now the evil question you can ask is, how does this homotopy operator behave with respect to multiplication? And then you have to write down another operation which has now 4 inputs and a relation. And now we play a sort of pattern matching game, which is we box in our relations and we ask, how are these 3 relations examples of the same one thing? And the answer is that this has an internal edge that I can contract. I should have drawn more dots. I was a little lazy. I should have drawn this as a dot and that's a dot. And you'll notice that all 3 of these trees are the 3 different ways of inserting a dot, an internal edge into this tree. And now the most interesting one is that these are the various ways of inserting an edge into this tree. And now that tells you what the relation ought to be in J. So an A-infinity algebra is a vector space A equipped with a sequence of maps mu(n) from A tensor to itself n times into A, which satisfy a sequence of relations, the A-infinity relations, one for each these are called corollas. So one for each tree with a single internal vertex in it. You sum all the different ways of inserting an edge in that and have that relation to be 0. So that's what an A-infinity algebra is. And what's remarkable about these creatures is that they keep coming up in mathematics. So they first came up in homotopy theory, the homology groups of loop spaces, but they keep coming back. So we in symplectic geometry, we love
These planar trees.
What's that? Planar trees, yeah, planar trees. In symplectic geometry, we love them because when you're counting pseudo-holomorphic n-gons, and you look at then counts of pseudo-holomorphic n-gons give you an A-infinity operation, and these A-infinity relations just come from when you compactify the spaces of holomorphic maps of the n-gon into your space. So let me do a very specific example. Let's think about holomorphic maps of the quadrilateral, which I'm going to draw for some reason like this. Holomorphic maps of a quadrilateral into your space, where this is along one Lagrangian, this is another, and this is another, and this is another. Well, if you have one-dimensional spaces of holomorphic quadrilaterals, and they can degenerate by having bigons bubbling off any of these 4 corners, or the modulus. This is a rectangle. It has a modulus. Its modulus could go to 0 or it could go to infinity. So when a rectangle's modulus goes to 0 or infinity, those correspond to these 2 ends of this moduli space. And those correspond to these 2 types of associations. So this is why A-infinity algebras appear in symplectic geometry. And then there's a deeper philosophical reason, which is that if you accept that DG algebras are fundamental mathematical objects, then there's a basic algebraic lemma which says that the homology of a DG algebra, so you lose information when you think you lose information when you take homology, but you can recapture that information by thinking about the underlying A-infinity structure. The same as the homology of a differential graded algebra is an A-infinity algebra with whose A-infinity structure is specified canonically up to isomorphism. So that's why somehow that's I guess why A-infinity algebras are fundamental mathematical objects, I guess. Okay. All right. So what I want to do now, at that long introduction, I want to find I erased it, sadly. What I wanted to do was I want to associate A-infinity algebra. Oh, sorry. There were other objects that I had mentioned here. One of them are A-infinity modules. So an A-infinity module is something that you have over an A-infinity algebra, but that's a module n, which has a differential on it, d squared equals 0. It has an action on it, which is a map from M tensor A into A, which I'm going to pick up. My module strand is going to now be blue. So in comes an algebra element. It satisfies a Leibniz rule like this. It's almost associative, except up to homotopy. So somehow A-infinity modules are sort of the natural module analogs of A-infinity algebras. So that's what was associated to a three-manifold with boundary. But now I would like to, the other object that I wanted to talk about were weighted A-infinity modules. So weighted A-infinity algebra. A weighted A-infinity algebra is a very small elaboration of an A-infinity algebra where instead of having dots, you write integers. So your trees, So there's I want to have my operations now will not just be indexed by how many inputs they have, but there's also going to be an additional integer called the weight, non-negative integer called the weight. And the A-infinity algebra, the infinity relations now will correspond to some number of inputs and a total weight. And when I insert an edge, then I want to have kind of weights to distribute. So like I want, you give me W, then I want the sum over all the different ways of A plus B is equal to W here and here, here, and so on. And there's one additional thing that I want, which is I want to allow, so far I didn't have any no input operations, but now I'm going to allow kind of, as long as I have at least any weight coming in, I'm going to allow kind of bubbles with no other input, just weight. So this is what a weighted A infinity algebra is.
Can you illustrate for mu 2 or something like that?
Yeah, what I want to actually illustrate this with is a real example. I want to give you now an example of an A infinity algebra, a weighted A infinity algebra, and then well, for mu 2. You want it for mu 2?
For mu 2?
I'll give it for mu 2. So like there's for mu 2, except now mu 2 has a weight on it. So maybe I put 3 on top of that.
Are you sure it maps to A? M tensor A goes to.
It's now for mu 2 is a map from mu 2 7, weight 7, is a map again from A tensor A into A. And the A infinity relation now looks like all the different ways you can split 7 into here, all the different ways you can split 7 into here, and all the different ways you can bubble off split 7 into over here, here. It's a sum of these oh, and there's 1/3 time term that I didn't put in. So if I had written dots instead of circles, then it was a familiar A infinity relation, but now I'm going to have to like sum over all the different ways of splitting 7 into 2 things. So this is going to be like a sum 2 plus 5, 1 plus 6, and so on. Okay? Sum of a bunch of terms. It's one of the problems with this subject that there are too many terms. But that's how it works. So let me give you now a particular A infinity algebra, which is relevant to the torus. So first I'm going to just describe an A infinity algebra, but without weights. So if I only look at the weight 0 part, that gives you an A infinity algebra. So let me start with that. So I'm going to draw the following. So what I want to draw is, here's the torus, and I'm going to draw 2 curves on it. And I'm going to think of this as a 2-manifold with boundary. And I'm going to mark these 4 sectors in the boundary like this. Okay? So this I'm now drawing the universal coupler. Okay? And what I want to do is I want to draw a path algebra which is going to have 2 idempotents. This is idempotent A and this is idempotent B. Or this is idempotent A and this is idempotent B. And I'm going to think of these 4 numbers as indicating 4 possible chords. There's a chord that goes from, there's a chord I'm going to call row 1, which is this 1 chord that goes from A to B. And there's a chord, row 2, that goes from B back to A. And there's a chord, row 3, that goes from A to B. And there's a chord, row 4, that goes from B back to A. So this is just like, I've got these 4 chords. And I'm just going to look at the path algebra. I can go round and round and round and round. So I can go, there's a chord that goes row 1, row 2, that goes from A to A. So that's this path here, this, here, here, here. Right? And there's a chord that goes from 1, 2, 3, that's here to here to here. Now, what I can't do is I can't go from 1 to 2 and then from 4 to 1. When I go from 1 to 2, I'm stuck over here. So what I want to do is I want to take the quotient of this path algebra by saying row 3, row 2 equals 0, row 4, row 3 equals 0, and row 1, row 4 equals 0, and one more, row 2, row 1 equals 0. So it's a quotient of a path algebra. That's my algebra. Okay? That's the algebra that we're going to work with. But I promised you an A infinity algebra. So what I have to do is I want to define some higher operation. The higher operations in this case are going to count maps of the disk into this punctured torus, which are branched covers, but all the branching happens on the boundary. And let me say it in very simple terms. Here's an example. There's this tile maps right here, and it goes 4, 3, 2. I'm going to mark my disk in a point, and so there's this map that maps, it covers most of the torus, and when you traverse the boundary, you see row 4, comma row 3, comma row 2. So mu4 of that should be equal to U times the left idempotent of 4, which I guess is B. So there, 4, 3, 2, 1. The key point here is that row 4 is non-trivial on this sequence: row 4, row 3, row 2, row 1. Now I put the base point here. I could put the base point there, and then that would tell us. Then we walk around this way, and we would find row 3, row 2, row 1, row 4.
Excuse me.
Yes.
What does UP and UA mean?
What's that?
What the results in the last two equations were UB and UA. What do they mean?
Oh, I'm sorry. So A and B are both idempotents in my algebra. So my algebra is this path algebra over here. B means somehow this stationary path over here. A is the stationary path over there. And U is in the ground ring. So U is a formal variable in the ground ring.
Okay.
Okay?
Okay. The same U as last time?
Yeah, it's the same U. We always have the same U.
Okay.
Unless you set it to 0 and then the mu4 dies. Okay. Now, there are two more terms, which are the two other cyclic permutations of this. There are some relations that, what should I say? Here's another lovely branched cover of the torus. It looks like it's a degree 2 branched cover. And when you go around its boundary, you see a different sequence. You see row 4, row 3, 4, row 3, row 2, row 1, 2, row 1. So there's a mu6. And that spits out now u squared. So the exponent here is the degree of the cover times, again, the left idempotent. And you can now imagine that this is a completely concretely realizable, it's like a Tetris game. You know, you put down some tile, some disk on the plane. You just read off the boundary, your sequence of chords, and that tells you an operation. And the U power just tells you how many tiles you use to write down that operation. This is not the whole A infinity action. There are other things that follow immediately. Like, for example, you can multiply row 2 on the left, then I'm going to have a row 2 coming out. So that follows from the A infinity relations. Like, I've got 4, 3, 2, 1, and I've got 3, 2, 1, 4, and over here I put 2. Well, this spat out u times the idempotent, so that should be non-trivial. This has to cancel. This tree has to cancel against something. And it's not very hard to convince yourself that there's only one tree that it could conceivably cancel against, and that's this tree. The only tree that's not obviously somehow 0. So we have to throw in an element like that spits out a row 2. So these are called left extended operations. I told you all the operations that spit out idempotents, and they have to be left extended or right extended. So that's now I've now described the entire A infinity algebra, and just bear in mind that A infinity algebra is not just a purely formal creature. It's measuring branched covers of the disk, which incidentally are also holomorphic curves of this sort. Okay, weighted A infinity algebras. Where did the weight come from? So the weight comes from, if you want to enlarge your class of covering spaces, so that observe that so far I was very, very careful to avoid this puncture, which I thought of as a boundary component. But if you allow your holomorphic curves to cover that in the interior, then you'll have these kind of Rabe orbits in the interior of your disk, and those are counted by the weight. So let me just give an example. I'm not going to write down the chord sequence, but you see this kind of operation, which maybe is a mu12. Right? So I go, like, let's say I start out over here, go row 2, then I go 1, 2, 3, 4, 3, 2, 1, 2, and so on. That's an example of a unweighted, very large mu operation. But I could bury this orbit. And if I bury that orbit, I want to think of this as a valid mu operation that I'm counting, but now it's going to have weight 1 because it's got this puncture sitting right in the middle. And now our weighted A infinity algebra is going to allow for, you now draw this sort of arbitrary picture in the plane, and we're going to allow ourselves to have in the interior various of these orbits, and those are going to count for the weight. Okay, is that a clear definition? So the problem with A infinity algebras is that sometimes it's hard to be friends with one, but this one is completely friendly. So you can just stare at it. There's an even nicer description of it if you think about the dual graph to these tiles. This is an A infinity algebra, which is determined by you draw a graph in the plane, which is 4-valent, and you mark you sort of consistently mark chords around the each vertex, and now you start out here and you traverse, and you multiply together the chords you see over here, then you put a comma. And you multiply together the chords you see here, put another comma, multiply here. So you can actually just sort of describe this in a completely complementary way. Okay, so it's unfortunate that I've erased this, but that's at least the algebra that we want to associate to the text. To a say some more things. To a three-manifold with torus boundary, I wanted to define a right-weighted A infinity algebra over that weighted A infinity, sorry, right? Weighted A infinity module over that A infinity algebra. So remember, what does that mean? That means that we have a vector space, which is the Floer homology of that three-manifold with boundary. You give me a weight W, and then you give me a bunch of algebra endings. And that's supposed to, so you give me so earlier you saw chain complexes. Now we see an A infinity module. So that means that we have an element of this this vector space. And you have a sequence of chords coming in. You have a weight, and that's going to spit out for you another element of this vector space. And that satisfies the weighted A infinity module relations, which are, which I could write down. But rather than doing that, I want to give you a special case. Bring it to life. I'm not describing how to define these modules. It's kind of ugly to say in general. But instead, I'm going to give you a special example, which I think will be illustrative. So, this was the maybe this is the picture I should draw. Okay, so this is the picture this was the basic tile that I drew. I've now glued that. What I want to do is I want to introduce another curve. I'm going to call this beta, and I'm going to call this alpha 1, and I'm going to call this alpha 2. So there's a single intersection point here. So by the way, this so we have to generalize the notion of Heegaard diagrams to bordered three manifolds. This is a bordered Heegaard diagram for the solid torus. And this intersection point P is the single generator of that module. So I want to now define an A infinity module with a single generator P. And what it's going to have is it's going to have some actions by these algebra elements. So maybe I'll draw the picture now over here. I'm drawing the same picture, but now it's maybe a little bit easier to see what's going on. And I hope I'm drawing the same picture. This is identified with this is identified with this, and this is my single generator. And what you see in this picture is, I was talking about holomorphic disks, and I didn't want to go too much into that, but, well, this is the torus. This is a disk. And by the Riemann mapping theorem, you can think of it as a holomorphic disk. It's a holomorphic disk that goes from P to Q. And as I'm traveling along the red boundary, I pick up this chord row 4, and then I pick up this chord row 3. And out goes P. So the way I'm going to draw that in this picture is that here's P, here's row 4, here's row 3, and out goes P again. So this is an action on this module. And you see another action, which is this disk right here. There's row 2, row 1, in comes P, out goes P. Now, I was trying to sell you all A infinity relations. So what do A infinity relations tell you? Well, if I do row 4, row 3, P, out comes P, I can do row 4, row 3 again. This is a term in an A infinity relation. It has to cancel against something. It's not very hard to see that there's only one thing that it could even conceivably cancel against, and that's this. Row 4, row 3, 4, row 3. But that is an actual holomorphic disk which covers this region twice. You can visualize it, but it's probably easiest to draw it in the universal cover again, as this picture. this is row 4, row 3, 4, row 3. And so this is a thing in the in this A infinity. This is an action in the A infinity module. What else is there? Oh, by the way, the A infinity relation, which says that these two terms have to cancel, is something that one can verify by looking at one-dimensional moduli spaces. So this is a zero-dimensional moduli space of holomorphic disks. I'm looking at a holomorphic maps from the standard strip into here, modulo R action. Well, there's only one. But if I put two next to each other, then there's a one-dimensional moduli space corresponding to this cut. And the cut can do two things. The cut could go all the way out to the boundary, in which case we get a term that looks like this. Or the cut could go all the way down to 0, which brings the 3 and the 4 arbitrarily close to each other, and that's that end of the moduli space. So this A infinity relation is the consequence of looking at boundaries of one-dimensional moduli spaces of holomorphic curves. But A infinity modules, why an A infinity module? Well, I told you there was this action row 4, row 3. There's also this action row 2, row 1. So something has to cancel if I do row 4, row 3, followed by row 2, row 1. And nothing multiplies, so that's a problem. But there's a mu4. And this u is somehow in the ground field, so it takes p to u times p. So that is, and maybe there was a little point that I should have told you about. There's a base point out here that picks up the u. So this actually is u times p. Row 4, row 3 spits out a u times p. So we needed this mu4 in order to construct a sensible module that satisfies something like d squared, an A infinity module. And you can also see that geometrically as follows. Here's row 4, row 3, and then I'm going to follow that by doing row 2, row 1. And now again, we have a one-dimensional moduli space of holomorphic disks. The cut point can go all the way out to the boundary, and that's the row 4, row 3, followed by the row 2, row 1. Or the cut could go to 0. When the cut goes to 0, the kind of object that you have is no longer a bicolored holomorphic disk, but rather it's a bicolored holomorphic disk with a totally red disk bubbled off on the side. So this is row 4, row 3, row 2, row 1. This kind of behavior is familiar in symplectic geometry. These are sort of like Fukaya Ono Ota O studying, the failure of d squared to be 0. We're counting these kind of holomorphic disks with boundary entirely in one Lagrangian, and that's a sort of highfalutin object. But in this case, they're just certain branched covers of the torus. All right, are there any questions?
And so how it's related to operations in Fukaya category?
Well, so I mean,
So where are Lagrangians?
Okay. All right. So to translate this into sort of the usual Fukaya story, these Lagrangians are the objects, and we have laid chords. I guess in the literature, one can look at the wrapped Fukaya category, and now this row 4, rather than being a chord, becomes then a generator in the wrapped. The morphisms from this curve to this curve in the wrapped Fukaya category. So this is identified with that. This story with weights is something that I think is sort of currently being developed in the world of Fukaya categories by Sheridan and others, but I think this has not maybe made it into the mainstream yet. The world of categories. Any other questions? Okay.
So this formalism makes it easier to compute?
This formalism, so why on earth are we doing all this? What I'd like to do is I'd like to have that same picture that we had for the hat theory. I'd like to have that theory in general. And then, yes, that would then be a formalism for computing. It's also a formalism for, it's also a conceptual framework. Rather than being, there are these holomorphic disks that you try to compute, you have a sort of general picture into which the theory fits. So it's, I would say it's both of those, and it is right now neither of them, right? So, except, I guess the torus case gives you an idea of what the formalism ought to be. I want to. Yeah.
Supposing you have a three-manifold and you have a bunch of things in it, maybe surfaces,
Okay.
for which there's some meaningful sense in which you want to think of them as being holomorphic objects.
Okay.
Maybe the three-manifold is also sitting. It's a four-manifold. It's an
Okay.
almost complex structure and some of these surfaces.
Okay.
Can you reinterpret those surfaces in terms of algebraic objects?
That I don't. That I have no idea what holomorphicity would translate to in this world. What if you have a surface that decomposes your three-manifold into components, then that surface has an algebra, and what you've done is you've realized your Floer homology is the tensor product. That's what I see. Any other questions I can fail to answer? I'd like to tell a story now in my remaining 3 minutes, which is why on earth a theorem like this should be true. Why would you get a kind of tensor product description? And let me start by saying what analysis gives. Analysis gives that if you have a Heegaard diagram and you pinch it along a curve where you've got these 4 alpha curves that are coming through, alpha 1, alpha 2, alpha 2, then you can define the holomorphic curves in the whole story. You can describe them in terms of holomorphic curves on the 2 halves. And let me just be a little vague about what's going on, which is that I got a holomorphic curve on the left side, a holomorphic curve on the right side. The holomorphic curve on the left side goes out and it meets the boundary along these various chords. The holomorphic curve on the right side also goes out and meets the boundary along exactly sort of the complementary chords. And our holomorphic curve is going to have the property that these relative distances match identically. So I'm going to have a configuration of points on the line from the left, a configuration of points on the line from the right, and they're identical. The distances are the same. So what that tells you is the holomorphic curves on this big thing are a fiber product of the holomorphic curves from here and the holomorphic curves over there, fibered over this kind of configuration space of points on R. And now, when I'm communicating, I've got my holomorphic curves here and I got them over there. They're communicating to each other real parameters, which are distances. Those are not algebraic objects. This is not something that's described in terms of the left-hand side or the right-hand side. It's somehow, there's the thing on the left-hand side and the thing on the right-hand side, and they're communicating to each other some continuous information, which is not algebra. So what I want to do is I want to turn that into algebra. And the game for turning that into algebra is I'm going to now draw both of those points. I'm going to just draw this picture. I've got 2 n-tuples of points, and they're living exactly above on top of each other. What I want to do is I want to sort of push some of the chords away from each other with respect to the others. And and I want to take a kind of limit as, so what I'm actually going to work in is, there's this space, which is the space, the configuration space. This is the associahedron, the configuration space of n tuples of points on the plane. And I want to convert a question, which is, so I want, basically what I want is a homology between the honest diagonal in here with a cellular diagonal. And that's the object that turns this problem, this geometrical problem, into a algebraic problem. So that once you get a cellular approximation of the actual diagonal, then you can describe these matched curves equivalently in terms of some object that's on the left and some object on the right. So that's probably all I can say about that now, and probably I should stop.
Where should one go to learn about the story that you talked about today?
I should write that paper.
All right.
Yeah, that's probably. I mean, well, of course, there's, we have an algebraic paper that sets up sort of the algebra behind all this story, which is based on people who came before us. So the theory of these algebraic diagonals was set up by Sanabulidze and Ubenbol, and we have a paper with Robert and Dylan called Diagonals of A-infinity algebra.
And at the very least, the notation in your paper is consistent with the rest of everything else.
Yeah, so that's a very long paper, which can be safely skimmed. Like there's a whole lot of theorems about finding diagonals, which have this feel of kind of the Eilenberg-Zilber theorem.
Yeah.
Where like it's like the general principle is that if you have a chain complex with trivial homology, then every cycle is the boundary of something. It's like that principle gets used over and over again. It's this very, very sort of conceptually simple, but it fits together into this story. So I was talking here about configurations of points. In actual fact, we also have orbits which are floating around as well. So it's a slight elaboration of the usual associahedron. We call this the associaplex. It's the object that you get when you try to find configurations of points on the disk.
The same level of holomorphic curves when you glue two things. Is it some gluing of curves or? So what is
The gluing of curves is what gives you the identical conditions. And then when you deform the diagonal, you're not gluing anymore. So what you want to say is that this is a chain complex that gluing gives you, which is exactly matched curves. And what you want to say is that chain complex is chain homotopy equivalent to a different chain complex, because you can extend your holomorphic curve theory into slightly more general types of configurations that don't necessarily have to be matched. So roughly speaking, the gluing is really only for the identically matched curves, and the rest becomes sort of abstract nonsense in some sense. By the way, I should have also mentioned there's this paper of Ganatra and Pardon, and Shane about describing the Fukaya category of a product as a tensor product of the Fukaya categories of the two factors. And this is a very sort of can be thought of as another way of thinking about that same story. So like if you're thinking about holomorphic n-gons inside of a product of two symplectic manifolds, then those are n-gons in one and n-gons in the other, and their moduli agree. And what this deformation is doing is that you're deforming the modulus of this with respect to the modulus of that, so that in the end you're counting something that has an algebraic description.
questions. Any other questions? Thank you again.
Bye.